Hi everyone, let's start chapter 9 on what I would call discrete math, which is the Math 245 course at Mesa College. The computer science people take that one. Although you're going to see a lot of the stuff in Calculus 2, Math 151, in the context of sequences and series. Calculus tends to deal more with continuous mathematics, where we have y equals f of x and things like that, finding areas and such. And calculus tends to deal more with that kind of continuous mathematics than discrete mathematics. This stuff with sequences and series, it seems like a different part of the calculus sequence. Now, what's the difference? Analogies may help the most. Discrete is digital. Continuous is analog. In other words, discrete is like a dripping faucet. Drip, drip, drip. Continuous is running water. Discrete math tends to deal with things that you can list, even if the list is infinitely long. The idea with continuity is that between two distinct pieces, you may have another piece. It's that kind of idea. All right. Section 9.1 on sequences and series, and section 9.6 on counting principles. I'm using the section numbering from a Larson textbook. Part A, sequences. Now, an infinite sequence can usually be thought of as an ordered list of real numbers. And it is often denoted by either this kind of list or this kind of list. Here in this list, the initial term is a sub 1. Then we have a sub 2, a sub 3, and so forth. Each of these a sub I guys represent real numbers called terms. When I have a sub I here, I is just a generic superscript. I is just a generic subscript. It's not the imaginary unit. It's not the square root of -1. Remember, we keep it real in this last part of the class. But here's a sub 1, a sub 2, a sub 3, a sub 4, and so on. There are infinitely many terms in this infinite sequence. A finite sequence isn't so interesting. Here, in calculus, you often start with a sub 0 or a naught, and then a sub 1, a sub 2, and so forth. That's why I often refer to either the a sub 1 here or the a sub 0 here as the initial term. The first term listed in the sequence. And even then, if someone were to say, what is the first term, this is clearly the first term over here, but someone could legitimately say, well, is this the 0th term? And is this the first term? Well, to avoid the confusion, let's just call this here the initial term for this sequence, and this here the initial term for this sequence. Now, if we're lucky, there's a nice pattern to our sequence of numbers, a pattern that we can describe using simple mathematical expressions. So for example, let's say that you're given this general nth term formula for a sequence. Write the first 3 terms of the sequence with general nth term, a sub n equals n cubed minus 1. Now, this idea is very similar to the idea of f of x equals x cubed minus 1. Again, it's the difference between discrete and continuous. When we had f of x equals x cubed minus 1, you're thinking that snake, right? I hope you are. I hope you remember the snake. Y equals x cubed minus 1, right? A snake that's lowered by 1 unit. And this is a continuous creature here. F is a continuous function of x. And we have this piece of string, right? This snake here. This here is discrete. A sub n equals n cubed minus 1. Now, in both cases here, you're going to plug in. Here, we plug in values for x. Here, we plug in values for n. But here, we can plug in values for x that aren't just integer, 1, 2, 3, and so forth. We can also plug in pi or 1/2 or the square root of 2, right? Whereas here, we only plug in integers. A sub n equals n cubed minus 1, where n is an integer. So it turns out that the graph is going to be a sequence of points, a sequence of dots. So again, this is continuous, this is discrete. Plop, plop, plop. All right. Assume that we begin with n equals 1. And in a pre-calculus class, you normally start with n equals 1. Although again, in calculus, you actually start with n equals 0 quite often. All right, so here n equals 1. This is kind of the flavor of f of 1, sort of. Right? You plug in 1 for n. A sub 1 equals n cubed minus 1 becomes 1 cubed minus 1, and that's 0. So a sub 1 is 0. That's the initial term of the sequence. For n equals 2, a sub 2 equals n equals 2. That's cubed minus 1. Result is 7. Plug in n equals 3. A sub 3 equals 3 cubed minus 1, and that's going to be 26. So the first three terms are 0, 7, and 26. And since we're starting with n equals 1, there's no ambiguity as to what we mean by the first three terms. And again, we can graph terms like so. We can graph terms in the sequence versus n, graph a sub n versus n. So n equals 1, 2, 3 over here. A sub 1 was 0, a sub 2 was 7, a sub 3 was 26. And by the way, you can think of these as beads or pearls along this string. So, and in fact, sometimes in calculus too, when you consider a sequence like this, a sub n equals n cubed minus 1, one strategy that you use sometimes is that you consider the continuous analog of that. F of x equals x cubed minus 1. And the idea is that the beads or pearls here are like beads or pearls on this snake, this string. So all the points here lie on here. And then you can make an argument such as the notion that since this thing approaches infinity as x approaches infinity, then these approach infinity as n approaches infinity. You can talk about properties like those, like long-term properties. Right? Calculus often deals with limits, like long-run limits. All right. No, actually, we won't be doing so much point plotting in this class. I mean, this is pretty rudimentary as far as that goes. Oh, and we sometimes call this the discretization of the graph of y or f of x equals x cubed minus 1. So this is a discretized version of that. Where the domain is not all reals. Here, the domain is assumed to be R, the set of all reals. Here, the domain is the set of positive integers. The domain here is a set 1, 2, 3, and so forth. The domain is a set of positive integers. And in this sense, sequences may be thought of as functions. Functions where the domain is, say, the set of positive integers. And, you know, just like with these guys, we plug in values to get what we want, these values. Next up, sign alternators, which we see a lot of in Calculus 2. Next time.